So Justin is a senior staff scientist at the LPI. He's also the manager for geology and petrology of that institute. Before that, he was associate professor at Southern Illinois University for several years. He did his PhD at Stony Brook University. And his dissertation, Constraints on the Chemistry of Martian Magmas. And I think, is that the one where Marjorie was on your committee?
No, Marjorie,
Margie Chan
was the PhD advisor of Sally Potter McIntyre, who's a co-I on my current P-STAR grant, but I'm not going to be talking about that work here.
Okay. Anyway, Justin has a wide range of interests, including volatiles on Mars, in Mars, petrology and origin of Martian meteorites, geochemistry and mineralogy of the surface of Venus, and magma sediment interaction on Earth and Mars. And just recently, he is the lead editor on a book that just came out, Volatiles in the Martian Crust. And that is available on Amazon. And
the cover's behind you.
Yeah. So today he's going to talk about constraints on the Martian volatile budget. So thanks for coming.
Thank you. Thank you for the wonderful day and the invite. So today I'm going to be talking about volatiles in the Martian magmas, change my title a little bit, and the interior, constraints and some open questions. And as I was talking to many of you, I realized that this is a topic I started in my postdoc 13 years ago, and came to fruition and sort of, at least at the moment, is ending with this book that came out last year, Volatiles in the Martian Crust. So a lot of the information we'll be talking about is sort of summary from this. We also had a special issue of Meteorics and Planetary Science journal back in 2016, Volatiles in the Martian Interior. So a lot of this comes from these two big sort of summations that we've done over the past year. Before I start though, I know many of you are not planetary scientists. NASA and planetary science loves to use weird names and acronyms. I will try to explain all of them. I know I will forget some. Please do not hesitate to raise your hand and say, I have no idea what that acronym or that word means. I will not be insulted. I will explain it before I move on. So I have tried to bring all of that information into this talk, but I'm sure that I missed something and some weird words, so please stop me if there's a word you don't know or an acronym. See, I already have one up there. University Space Research Association, it's the nonprofit that runs the Lunar and Planetary Institute. So I already have one acronym up there that I don't know. So what is the big picture question that I've been going after? And the issue is, what is the input of magmatically degassed water into the Martian water cycle? For planetary exploration, one of the big questions always is Mars habitable? Was Mars habitable 4 billion years ago? Could it still be today? And then that leads to the question of, is it habitable? But before that, we need to know, where did the water cycle come from? And one of the big constraints for habitability of a planet is degassing of a planetary interior, which means we need to know how much water was in the interior. And you can see in the background here, this is actually a water map of the surface. And so the brighter colors, and I know it's sort of grayed out, and I'll show this in better detail in a few minutes, but we know that there's water on the surface, and it varies from the poles to the equatorial regions. But where did this come from? Water in the interior is vital for habitability of a planet and degassing. Our Martian meteorites, our best hand samples we have of Mars, and I'll go through in a second which ones we have and the information, have almost no water. They're about 50 to 100 ppm water. And so the big question is, were they from a water-poor mantle, in which case all the water we see on the surface was added by comet impact or other impacts onto the surface and is not actually Martian water? Or were they degassed, which meant we did bring water to the surface, in which case we have water in the Martian interior and we have evidence where we have the needed water. So what data sources do we have? And here's where I'll go through some of the background of the information, and hopefully we won't get too heavy on jargon, but again, stop me if I don't. We have three main sources of data for Mars. We have orbital analysis, where we can send an orbital spacecraft around Mars and we can measure the surface. We can look at it with imaging, we can look at it with spectrometry, We can even measure different elements on the surface of Mars. We can map those. We have our hand samples, our Martian meteorites, or our SNC, and I'll explain what the SNC stands for, but it's just the abbreviation of the type specimens. Sugartite, nachtlites, and chastamites are 3 main types of Martian meteorites. And there we can do the exact same type of analysis that we can in any geology lab. We can look at mineralogy, we can look at volchemistry, but the issue is these are meteorites. We don't know where they were from on Mars, and they flew through space and went through space weathering, they went through atmospheric entry, they went through shock processes, so they're not necessarily pristine fresh basalts like we go to Hawaii to understand the material here. And then our third, and I'm not going to really focus on this for this talk because this data doesn't place huge constraints, although a little bit, is in situ rover analysis. And so we've had, over the past, since 2006, so the past 14 years, a slew of rovers on the surface of Mars, from Mars Spirit and Opportunity to now Curiosity, and hopefully in the future, Mars 2020, which is going to launch this summer, and Rosalind Franklin, our European Space Agency rover. And so we have a lot of data there that can also play into this. So let's start with orbital analysis. What information do we have of volatiles, not in the interior, but on the crust of Mars? Are there volatiles, and how much? And so here are these are 2 of my favorite maps. Water and chlorine. Unfortunately, the GRS team, when they publish them, makes the water map circle and the chlorine map square. You can see similar features. So one of the big things to point out, here are large volcanic provinces. So this is the largest volcano in the solar system. Here's the other 3, and then this is our other large volcanic province over here. You can see water high at the poles. We've got ice caps at both poles, a mix of water and CO2 ice. Equatorial region, we have lower water. It doesn't go quite to 0 in most places, but it's pretty low. And then chlorine is quite high. It's between 0.2 and actually over 1 weight percent. And unlike water, which is high at the poles, well, first of all, we can't see the poles because there's so much water that we can't really see anything else, and so they're cut off. But at high latitudes, we have very low chlorine. Instead, and this is something we're going to come back to a lot in this talk, in the volcanic province here, and to a lesser extent, but still some extent here, we've got very high chlorine concentrations. And so this is suggestive already of chlorine coming from the interior. Water is not correlated here. Water is not correlated with volcanic regions. And so this is an interesting thing to look at as we go forward. All right, our other data source, and the main one I'm going to focus on this, is our Martian meteorites. We have 3 main classes, and I'm going to talk about a 4th one briefly. This is the main type. They're sugartites. These are our basalts from Mars. They're mainly all about 180 million years old, so they're relatively young. They're basaltic rocks, so they've got pyroxene, olivine, and plagioclase. They're all fully crystalline. There's a few with a little bit of glass in them, so they are either thick lava flows or shallow intrusions, and they're similar to rocks you find at Hawaii, especially after you fully crystallize. The N in SNC stands for nachtlites. These are lovely brown rocks. These are cumulate rocks. They are mostly clinopyroxene. They're about 90% clinopyroxene, a little bit of olivine, and some plagioclase. There are not great analogs to these on the Earth. The best is a place in Canada called Theos Flow, where we see pyroxenite actually flows on Earth. We will come back to both of these moving forward. The third, these are the chastagnites. We, at this point, have 3 in our collection of these. These are dummies. So they are dominated by olivine, hence the green color, and apology for the pixelated picture. They're olivine cumulates. These are similar to what you find in San Carlos in Arizona. So olivine, they have beautiful melt inclusions, which is where we can get a lot of data from, a little bit of pyroxene and some potash. Again, all of these rocks are, if you include the nachtlites and chastagnites, about 1.3 billion years old or younger. And so this tells us about the recent past on Mars. We have one rock, or one sort of suite of rocks now, that was found a few years ago. This was nicknamed by Carl Agee Black Beauty. That's called NWA 7034, Northwest Africa 7034. We named rocks after where we found them. So this rock was found somewhere in Northwest Africa. It is a breccia. It has two main ages of 4.1 billion years and 2.1 billion years. And so this tells us that the classes within this are all different ages from somewhere between those two sort of epochs. The issue with this is it's a breccia. It's seen lots of secondary processing. The ground mass in this rock is full of water. So it tells us a lot about regolith processes, but it doesn't tell us very much about internal processes. And so our best rocks for understanding sort of internal process on Mars are the shergottites and the shastites. Our third data set is our Mars family of rovers. And when I was describing them before, I was focusing mostly on the twins, Spirit and Opportunity, and Curiosity, and then Curiosity's twin, which looks very similar to this, Mars 2020, which is being built right now and we'll launch this summer. But going back to the 90s, we also had Pathfinder Sojourner. So just for a scale, Sojourner was about the size of a shoebox. Spirit and Opportunity were about the size of this desk, maybe a little bit wider, but about this desk. This is about the size of a Volkswagen Golf. So we have now landed a car on another planet. Which also, when you get larger, you can bring more sophisticated technology with this, which is great. So this, all of the technology for analyzing the rover or rocks is right there. And so it literally had to drive up to a rock and more or less kiss it in order to analyze the rock. Here, we had an arm, which is sort of shown here. We also had spectrometers up sort of the eyes. And so we had mobility to move and also move our instruments around. There was also an abrasion tool, so we could actually grind into the rock to get rid of some of the surface grains. On the other hand, Curiosity and the follow-on Mars 2020 have actually instruments on the arm. There are instruments up here. You can actually see this red light. That actually is a laser that zaps rocks, and then we can measure the plume that comes off. And then in here are actually a mass spectrometer and an X-ray diffraction. So we can actually do mineralogy and actually noble gases and organics in the benchtop here. So we've gotten a lot more sophisticated with the instruments we send to Mars. So you wonder why I'm not using this data for this talk. Well, I'm looking at interior volatiles, and this is where we have sent all of our rovers. So map, our volcanoes are here. Our volcanoes are here. All of these spots, there's Spirit, Curiosity. This is InSight, which is a geophysics lander, Opportunity, Pathfinder, the two Viking landers, and Phoenix, which was also a lander. None of them are near the volcanoes. This was done for two reasons. One, a volcano has a slope, and if you land something on a slope, it's going to roll downhill, so it's really difficult to land on a volcano. And two, our biggest drive for exploring Mars is habitability. The biggest place to look, or the best place to look, is right where we've got this crustal dichotomy, where fluid is going to flow downhill. And so that's the reason we've sent these to these places. So this data is interesting, and you'll see it in a few slides, but I'm going to focus mostly on what we know from Martian meteorites. So this brings us back to sort of 1990s, late 90s, early 2000s. What was the debate back then? What estimates did we have? Well, there were researchers back then arguing that Martian magmas contained up to 2-8% water and comparing them to what we see in subduction zones on Earth, where we've got volatile recycling, lots of fluid, lots of CO2, explosive volcanism. And I will be fully transparent that I am either second or third author on this paper. Others, including multiple of myself, have suggested that they did not degas, but these are from a water pore source region, and instead there was some other volatile, and we'll get to what that was, that dominated this. And so this is the debate we're going to go through. And how do we resolve this? Well, we look at the S&C meteorites. These are our best data we have. We look at our mineralogy, so we look at minerals that can take water. Amphibole and apatite are our two best examples. I'll also go through some where we've got melt inclusions and actually have water measurements directly. And then we can look at bulk chemistry. Fluorine, chlorine. Fluorine is not very fluid mobile. It likes to stay in the rock, and so its bulk chemistry is pretty well constrained. Chlorine to a lesser extent. Water is the worry, because water loves to be in the gaseous form and not in the rock. But we do have bulk chemistry for S&Cs, and I'll actually show you some of the surface basalts, which interestingly may drive this to even higher concentrations. So how do we do this? Well, we're going to go through using some cosmochemical constraints on the chlorine to lanthanum ratio of the bulk composition. We can use this to calculate what was in the magma and then what was in its source region. We can use the water to chlorine ratio once we have this value to calculate the parent magma of these hydrospaces. So focusing on amphibole and apatite as well as the melt inclusion data to calculate water content again of the basalt, the magma, and its source region. We'll look at the fluorine to chlorine ratio to calculate fluorine. We'll compare it to the Earth to see how different Mars is than the Earth. And I'll tell you already that Mars is quite different than the Earth. And then if there's time, and if you're interested, we can talk about what evidence there is for degassing in the Martian meteorites. I have those as my last 5 slides, so if we don't get to them, you can ask them after. So how do we use cosmochemical constraints to understand sort of building a planet and differentiating? And so what we do is we compare a element that likes to degas, likes to be in the gaseous phase, a volatile element, with something that prefers a refractory element, something that likes to be in the crystalline phase. And then we keep everything the same. We make sure they're both incompatible, and it's just the volatility that we're ratioing. And so chondrites will always be up here. They'll always have much more volatiles than everything else because everything else has degassed when you're making a planet in comparison with the chondrite. So you'll have planet A, which degassed some, B, C, and so on. And this will have less volatiles than A, and so forth. And so that will bring you this direction. Once you make a planet, everything else that happens, assuming you didn't degas to the atmosphere, should drive you, or degas beyond the atmosphere, should drive you in this direction. So mantle melting and basalt fractionation won't change these two ratios. It will only go in this direction. So if we get these nice lines, that tells us that we haven't altered this some other way, and it tells us about the planetary element. And so the element we're going to focus on first is chlorine and lanthanum. One, because chlorine is relatively easy to analyze, and two, chlorine is not as volatile as water, which likes to escape much quicker. Plus, we have a lot of data, and we don't have as much data for water. So this is all of the data we have for chlorine to lanthanum and Martian meteorites. Now, I know most of you work on the Earth, and this is a tiny data set for one field site, let alone an entire planet. But it is the best we can do at this point. And it does, once you start looking through this data, actually show a nice line. So we've broken our data set into the same category we had before, our shergatites, and now we've got them broken apart by the enrichment or depleted version in terms of rare earth elements. That really doesn't matter for the talk, but it's another way to geochemically classify. We only have data for one of the chassignites, so instead of chassignites, it's chassigny, mafites, and then I forgot to mention that there's one other weird meteorite, Allen Hills 84001. It's 8.41 billion years old. It is an orthoperoxenite that has seen at least 3 evidences of shock. It has carbonates. It has seen lots of secondary processes. I've included it for consistency because we have so little data, but I would not put any trust in that data. So the first thing we can see is if we just take the data as a whole, we've got a scatter plot. So let's look through the data first. First of all, these 4 points all have high chlorine to lanthanum. They also have terrestrial alteration. And in fact, these 2 have salt crystals in them. If you take a basalt and add salt to it, you're only going to add chlorine and not lanthanum, and it's going to bring you up there. And so these 4 can easily be explained by addition of chlorine by secondary processing. We have 1 down here, and remember, if we degas, we're going to come off of this trend, and so this could be from degassing. I can't say I promise that I understand that data point at this point, but that is our best guess as to why this is lower. There's no other evidence for degassing, but again, none of these have vesicles, so it's hard to figure that out. Okay, so now if we remove these 4 data points and these 1, and I'm going to ignore the 2 yellow lines for a second, we have a nice trend right through here. So the rest of these give a nice chlorine to lanthanum value of 51 plus or minus 17, which actually is statistically pretty good. We have 2 that are higher that don't have evidence for degassing or extra chlorine in the form of salts or anything else. And so this may tell us we have a heterogeneous interior, but I wouldn't want to sort of bet on 2 data points. And so we really need more for that. But this is suggestive of something else going on with possibly even more chlorine in these magmas and in the source region. So let's compare this to the Earth. If we take the same thing and take basalts on Earth that either haven't degassed or have relatively little degassing, so things that have erupted underwater or under ice, or mantle xenoliths, we can plot those, and they plot here, and Mars plots here. And again, these are the altered ones, and this is the degassed one. For comparison, the basalts analyzed on the surface of Mars, the ones that were analyzed by Gusev crater, where we had rubbed away all of that alteration, plot way up here. And the newer data from Gale crater, which is where Curiosity is, plot actually even higher. And so this, again, is consistent with these 2 data points that suggests Mars basalts may actually even have more chlorine than we're getting in the basalts that we have in our collection, which is quite interesting. So if we use these ratios, we get a bulk chlorine abundance of 25 plus or minus 8 ppm, which is great that we can get a number, but what does that actually mean? And what does that mean in terms of the Earth? Well, first thing we can see, these are log-log plots, and if we look at this slope and we look at this slope, Mars is about 2 to 3 times more chlorine enriched than the Earth. And so we get a 2.5 plus or minus 1 times the value of the Earth. And just for comparison, sort of the terrestrial enriched upper mantle, so EMORP source region is about 30 ppm, right within our value of 25 plus or minus 8. The depleted mantle, so depleted MORB mantle is about 1 ppm chlorine, so we are over an order of magnitude higher. And so just to sort of get your mind sort of where at least bulk Mars is we're looking at an enriched in terms of chlorine. All right, so that's how we get to chlorine. That's the easy one. The next one's the harder one, is how do we figure out water? As I said, bulk water of these is 50 to 100. Unfortunately, those measurements don't correlate with anything, but we also only have about 5 or 6 of them. And the data is mostly from the 90s. So instead, we focus on looking at the Martian meteorites. There's one study looking at melt inclusions within olivine crystals and pyroxene crystals and measuring water directly. The rest of it, we have to get it another way. And the other way is to either look at amphibole or apatite, which take water, chlorine, and fluorine into the crystal structure, and we can back out what was in the magma, and then we can back out what was in the mantle source. So this is the data we have for melt inclusions, and this is Tomo Usui's work. The problem with melt inclusions is they're mostly crystalline. And so this is the olivine host. These are the melt inclusions. And if you were studying the Earth, you'd probably throw all of these melt inclusions out because there are cracks that go directly into them. There are cracks that come out of them. These are crystalline. These are not the types of melt inclusions that on Earth you would want to study. But these are the best we have. There is one here that is nice and glassy. There's another one up here, but that's not the norm. And so he found the glassy patches within these to analyze water, fluorine, chlorine, and CO2, and then backed out what the water content was. And I'm just showing chlorine to fluorine here, but the water correlates as well. He measured melt inclusions. He measured some of the ground mass where there was glass as well. And you can see there is a slight difference, and this is probably from degassing, where we're losing chlorine but not fluorine, or so we're going in this direction. Thankfully, the melt inclusions give a relatively straight line, although it's only 3 data points. And so again, I wouldn't want to extrapolate from that alone. And so let's look at our mineral constraints. And so the biggest one we have is apatite. Apatite has been found in almost every Martian meteorite. It's been now analyzed in almost every Martian meteorite. You can measure fluorine and chlorine by electron microprobe, so it's pretty easy. Based on those, you can calculate the water content. You can then back out the water content in magma. We also have amphibole in some melt inclusions, in most shergottites, in both of the chassignites, and in one knotite. And so I'll go through the amphibole constraints as well. So this is the Martian apatite data. So this is OH, fluorine, and chlorine. These are only in the shergottites, so these are only in the basaltic meteorites and not the cumulus. For comparison, I took, and you can go back to, this data is actually started in my 2009 paper and then updated in 2016 in the companion papers. But I've simplified it to a blue field here. This is terrestrial apatite of rocks that have not seen metasomatism, have not seen alteration, are not from subduction zones where fluids can change based on subducting slab. These are mostly from mid-ocean ridge systems in general, and ocean islands. And typical terrestrial apatites that have not seen secondary fluids plot right down here. They're typically rich in fluorine, and they follow along the fluorine-OH join. They have a maximum of a few weight percent chlorine, but not a huge amount. On the other hand, when we plot all of the data we have for the shergottites, you can see it's a much larger scatter, but with the exception of about 10 analysis, they all have much higher chlorine than the fluoro-OH ratio for the Earth. And if we get an average, the average is sort of right in the middle of this field where we have a chlor to fluor to OH ratio of 5 to 3 to 2, comparing again to terrestrial apatite with right around 0. There can be a little bit, but variable fluorine to OH ratios. And so this is consistent with Martian magmas being chlorine rich and water poor compared with their terrestrial magmas. Getting from apatite chemistry to magma to mantle source is problematic. We did it in these 2 companion papers, and I'll sort of put that into our table at the end. The other data source we have is amphibole. Amphibole is typically found within melt inclusions. So remember I showed you those melt inclusions that were nice and crystalline. Well, within some of those, we have nice amphibole. Here again, not a great beautiful circular melt inclusion, but we've got a melt inclusion here. This is in pyroxene and shergatti. We've got a large spinel crystal here, and this brown face here is amphibole, and this is about 50 microns across for comparison. This is one of the 2 chassignites, or one of the 3 chassignites now. This is NWA 2737. You can see the relatively euhedral olivine. It is now brown. The brown is from shock. So we know there's been secondary processing. In here, we've got a large melt inclusion, and it's a lot more circular. There's a 100 micron scale bar, and we've got a nice large amphibole crystal here. And we've actually measured this specific specific amphibole for chlorine, fluorine, water, and even D to H ratio. So in this case, we can do a lot more detailed analysis. So what does some of the Martian amphibole look like? This is the chlorofluor water content of the amphibole and chassigny. The one in NWA 2737 that I just showed you a weird one in MIL 03346, which is one of the knocklights. And this one is quite weird. LEW 8516 and Zagami are both Shogatics. You can see, I'm going to skip this one for a minute, they all have about 0.1 or a little bit less chlorine, 0.5 weight percent fluorine. And where we do have water analysis, and I know we don't have it in all places, it's relatively low, 0.1 to 0.2 weight percent. And if we use partition coefficients for the Earth, and we calculate what the fluorine, water, and chlorine concentration of the magma was, this is what we get. We get both the chassignites with water contents of less than 0.1, so sort of Ocean Island-esque, but lots of chlorine, 0.3, fluorine, it's a larger range depending on which partition coefficient you use, you get 0.1 to 0.5. And this weird knocklight, when you use terrestrial partition coefficients, you get 20 weight percent chlorine in the magma. That is way beyond the amount of chlorine that you can shove in a magma. And this tells you that this magma was degassing as this crystal was forming. And this crystal actually probably formed from that chloride brine or that chloride vapor rather than forming from the magma. And this is, if I have 5 minutes at the end, what I would go into is talking about what evidence we have for these heavy chlorine degassing. So amphibole, we know it prefers OH to fluorine and chlorine. Back in 2014, we published a compilation of partition coefficients for all of these elements between amphibole and melt. This is the issue, is it is temperature dependent. It is also dependent on whether the magma is degassing at the time or whether it is volatile undersaturated, which is the difference between the open symbols and the closed symbols. We also don't have very good data for fluorine, hence my larger error bar, but we do for chlorine and water. And we can put all of this together. Yes. We can put all this together to look at the water-chlorine ratio of Martian magmas compared to terrestrial magmas and the water content. And so this is water to chlorine ratio. This is from amphibole and melt inclusion. I'll add apatite into not the next slide, but the slide after. So you can see the estimates for water in Martian magmas goes up to 10,000 ppm. That's sort of the low end for the Earth, and the Earth starts there and goes higher. The other big difference is the water to chlorine ratio for Mars to the Earth is 0.5 to 4, whereas the Earth is 4 to 100. Water dominates magmatic systems on the Earth, at least most of them, with the exception of carbonatites and a few weird magnets. But when you look at Hawaii or rifting systems, water dominates. On Mars, chlorine dominates, or at least chlorine and water are equally dominant in these magmatic systems. So using this 1 to 0.5 to 4, we can calculate the water content of the Martian interior. And so based on this bulk chlorine concentration of 25 ppm, we get a bulk water abundance of 56 plus or minus 11. So what does that compare with the Earth? Well, the terrestrial enriched mantle, which is where our chlorine value is, should have about 200 to about 500 ppm water. We have 56. On the other hand, the terrestrial depleted mantle has 1 ppm chlorine. We're an order of magnitude higher than that, but it still has about 100 to 150 ppm water. So we are drier than the driest sort of source region on the Earth, but we're enriched in chlorine. All right, so what about fluorine? Fluorine's easy, we can measure it in bulk. It degasses the least of the three of these, so we can look at the fluorine to chlorine ratio to get this value. And we don't have much data for Mars. We actually have less fluorine data than we do we can go back to about 1 billion years, or 1.3 billion years. But we're missing 3 billion years of Martian history. What was the volatile content going back in time? Did Mars have more water and it lost it through producing magnets? We don't know, we don't have the data. And then something that we know that the Earth is heterogeneous, so why wouldn't Mars be heterogeneous? How heterogeneous is the Martian interior? We do have suggestions of this. You see the chlorine to lanthanum values and those high chlorine values. There is suggestion of even higher chlorine values in the Martian interior than the numbers I'm presenting here. It may even be 2 or 3 times that in certain source regions. And then something I didn't go into at all is isotopes. How do isotopes play into this? Well, interestingly, isotopes are not correlated with bulk values at all. So sulfur isotopes, chlorine isotopes, and hydrogen isotopes, so DH. What is that telling us about the Martian interior? It's probably telling us this, that the Martian interior is rather heterogeneous. And some of these may have been affected by secondary processes. But again, with the data sets we have, these are still hugely open questions. All right, are you interested to hear about how Mars degassed? Or would you like, okay. It's only a few slides. So, what evidence do we have of degassing of weird chlorine magmas? We know what happens when a terrestrial basalt dominated in water erupts. It produces a steam cloud. If there's a lot of CO2, it explodes. You might get some hydrochloric acid. You might get some hydrofluoric acid. But what happens when chlorine is the dominant phase? Well, in that weird knocklite that I was talking about, NIL03346, and its pairs of those 3 numbers, we have measured the most chlorine-rich amphibole ever measured, higher than anything we found on the Earth. In fact, I have a colleague, David Jenkins, who's been trying to make this in his lab, and he can't. He's getting terrestrial values in his lab, but he's not getting to the pure chlorine number. And so here it is. This is a melt inclusion again. This is in a knocklite, so this is pyroxene. You can see it's fully crystalline. Here's a chlorine map, a potassium map, and a titanium map. So this is titanium, iron titanium oxide. The potassium up here is either glass or was potassium feldspar and now glass. And then down here, these values down here are chlorine-rich amphibole. It is also potassium-rich, so it is quite weird. And so when we compare it with the Earth, with amphiboles from the Earth, here is chlorine to iron. These are atoms per formula unit in the amphibole itself. You can see most amphiboles don't have much chlorine, but you can see this is where Earth stops. This is the chlorine value in these Martian amphiboles. On Earth, these form in high-grade metamorphic terrains where you've got chlorine-enriched fluids moving through. You have to have a protolith that also has high iron and high potassium. Another place we have evidence for Martian degassing where we actually have better constraints on the PT conditions of formation is a weird mineral called Scapalite. And when we found this, this is the chemical formula. It looks like a plagioclase with chlorine in it. And so when we analyzed it, we thought we were wrong. We polished it, put it back in the microprobe, reanalyzed it, still didn't believe the data, polished it, reanalyzed it, still didn't believe the data, and we did it 4 times and kept getting the same results. So here's another melt inclusion, pyroxene hosted. Again, fully crystalline. Here's augite, there's glass, there's K feldspar, and down here is a sort of subhedral to euhedral, depending on how you look at it, scapalite. Now again, when we compare it with the Earth, here's chlorine, and here's the anorthitic component in this phase, because it's almost plagioclase. You can see the black symbols are all from the Earth. You can see the Mars symbols, and you can see how many times we analyzed it, and depending, since it's so small and you're analyzing it so many times, you're getting overlap. But you can see, again, we're at the high chlorine end number compared to the Earth. We do get these on the Earth. These are hydrothermal, but it is the phase Mariolin. And so it is consistent with either hydrothermal activity and or late stage igneous activity. And there's actually experiments on forming this chlorine-rich end member. And so here's pressure, here's temperature. Anything below this line has albite plus sodium plus chlorine in the system. Anything above this system has mariolite. Because we have pure mariolite in our system, we can use a simple phase diagram like this to constrain temperature. We don't have an estimate for pressure, so if we assume the surface, it's 700 degrees Celsius. If we go deeper, obviously it gets hotter than that. And so again, this is like that chlorine-rich amphibole. These are right at the transition of when a magma is probably degassing, and that degassing is interacting with the magma itself to produce these gases. And so this is incredibly chlorine-rich. The other thing is for both of these, if there was more water in the system, you would get something else. In this case, you would get an amphibole. In the case of the last phase, you would get more of a typical hornblende, and you would lose your chlorine to the gas phase. So this also tells us that the activity of water had to be near zero. And so chlorine-rich scapalite forms in the presence of NaCl fluid. The weird amphibole forms in the presence of potassium iron chloride fluid. So we're dealing with incredibly weird degassing compared to the other. Lower sodium chloride concentrations and higher water contents would produce a hydrous phase. This again combines with what we've already shown that show that chlorine has to be the dominant phase, or at least equally dominant with water in these systems. And so I can summarize my last 10 years worth of work, at least on this topic, on one slide. Mars, a chlorinated planet. Martian magmas were enriched in chlorine, probably about 2.5 times what the Earth values were. Eruption and degassing of these would have delivered chlorine to the Martian surface. This is also consistent with one of those first slides I showed you, where chlorine is higher in the volcanic regions. That's probably degassing. That's probably from these hydrothermal systems. And going back to the big picture question, chlorine-rich degassing is pretty noxious to most known terrestrial organisms, and it's not going to produce great assistance to Martian habitability. However, just like we see at Yellowstone and other geysers, as the fluid would have cooled, as it would have interacted with the crust, depending on what crystals formed and how it interacted, it may have become a habitable environment, but this is still a big open question. And again, this is still for young Mars. Going back in time becomes a lot more difficult. All right, thank you.